Last week, what we did is we used my analogy, central station, subway station, to partition a bunch of observation, and then you turn those observations into two different types of sum of square. The local commute, the error sum of square, and the subway station sum of square, the treatment sum of square. And there's two different types of sum of square. When you add them up together, a squared plus b squared equal to c squared. So it's kind of like Pythagorean theorem. And after that, I said that, okay, so the sum of square, you have this sum of square total equal to sum of square treatment plus sum of square error term. And then the degrees of freedom pretty much follow the same order, that total degrees of freedom need to minus 1, because if you have the central station or subway station estimated, the minute you start having that, where is my frame of reference, where is my central station, you have the average. The minute you have the average, you have one constraint to lock the 16 observation together, and so you lose 1 degrees of freedom. So the total degrees of freedom is 16 minus 1. And you have 4 subway stations. The minute you start saying that those 4 subway stations located based on this frame of reference, you lose 1 degrees of freedom. So it's 4 minus 1. So totally, whatever left for the error term is the sum of square total, the degrees of freedom total minus degrees of freedom treatment, you get a degrees of freedom error. Okay? And in order to get the proportion of the sum of square and over sum of square, you need to divide it by their degrees of freedom. And now you have your F statistics, 8.53 or whatever. Basically, it's the ratio of your MS over MS. Okay? Show hands. Everybody on the same page. Visualize everything. Okay? If you don't, door is over there. Okay? You need to drop this class because this is the fundamental. If you cannot visualize this, then the rest of the semester you're going to struggle. You have to feel it. Okay? Next. Okay? Today we're going to talk about this. So on one hand, I have sum of square over the sum of square, justified by their degrees of freedom. This value, if I want to say my subway station makes sense, then the numerator should be as big as possible. And the degrees of freedom left for the error term, the sum of square here, should be as small as possible. So this ratio I want it big, but how big is big enough? Beyond some reasonable doubt. And this is the reasonable doubt we would like to build. Okay? And so everything we try to build is that we said that, hey, I want to say that the subway station's location over the error term local commute location makes sense. And how can we say it makes sense? Must be big enough. And how big is big enough? Right? So the way how we do this is beyond some randomness. So the goal today is trying to establish the randomness. Okay? So last time I basically showed you that how to build. Yep. The classroom support is supposed to fix this problem, but I submitted application in June. So I don't blame the school. There are so many departments need to fix their classroom. Even this classroom, let me whine a little bit. Before we have all the chairs on caster with fabrics, do you remember? But it's not COVID safe. They say fabric is trap virus. So we have to remove all the chair. So no matter upstairs, downstairs, now there are the kind of chairs. Okay, and what I'm saying is that the classroom support is swamped. So bear with me. So right now, just remind me, use column E. Okay. Last time I talked about the how to build the bell shape, and I basically said that if you use a bunch of let me just use this. If you use a bunch of standard normal distribution, okay, use a bunch of sum of some random number, okay, and how to do this? Oh. Oh, here we go. Okay, and if I have enough of them, sooner or later I'll build a standardized normal distribution. So Control C, paste value. Okay. So if you use this, you can build a normal distribution. So you see the average, a standardized normal distribution, where is the mean value? Where is the standardized normal? Close to 0, right? And what is the standard deviation of standardized normal? Should be 1, right? So it should be very close to 1. And of course, this is my 10,000 sample, good enough, mean and average. And of course, if I use this random number times a scale, say, give me a scale, any number? 12. 12. Times 12 means that original bell shape is 1. Now stretch 12. And then plus a level. Where do you want a level be?
1.5.
1.5. Okay. 1.5. It's not bad, but it's hard to draw. So let me use 150. Okay. So now. This is the new mean and new standard deviation. Okay, so if I use this one, drill a bell shape, you see a 0, 1 bell shape. But if I use this one to draw a bell shape, you see a mean at 150, variation, standard deviation at 12 bell shape become a pretty stretched out bell shape. And then of course, if this is a real value, what you do is use the value minus the mean. If this value minus the mean divided by the standard deviation, what we call this a z-score, right? Right? Minus the mean divided by, and that will recover that back to our original bell shape. Okay, so if oops, what happened? Oh, need to lock it. Lock it. I received email and said that, can you review some of the Excel? That's none of my business. You go online if you don't know how to use some Excel function. There are some YouTube and stuff. I need to use the lecture for DOE, okay? And how to review Excel. The only reason I use Excel is I worked for industry before. Yeah, if I walk to industry places, and usually they don't have MATLAB, they don't have SAS, they don't have a lot of stuff. And if I need to do something and convince them I know what to do, what's the best way to do it? Show me your data. I'll use your computer, use Excel on your computer and get things done. If they see that, they trust you. But if you say, oh, I need to use my special MATLAB software, sometimes, to them that's a black box. Okay, anyway, I return this back, so this is the z-score. And so if I have one z-score, I square it. So let me do this for fun for a second. So if I only square one z-score, that's chi-square 1. And the bell shape of the chi-square 1 is basically every value be what? Flipped to the other side. So if you show data analysis, histogram, okay? And then from here to here. And then you will see a histogram looks somewhat like this. Okay? Pay attention to chi-square 1. Is there any negative value? Because it's square, right? Now, if I said, I don't want to just have one square, I want to have 3 square. So now, if I do chi-square 3, what I really need to do is, okay, here's 1 square, right? I'll have another 1 square. So this, no, S, I, and B. So this is a z-score. Oh. I need to have random number inside. Okay? Okay, and once I have that, this is another z-score square. And then I said that, let me have another one. Or let me have a bunch of them. But let me just have the first 2. Okay? Control C. 10,000. Huh? Why it's not happy? Oh. Okay, so here's one chi-square, here's another chi-square, here's another chi-square. Okay? And let me do this, just save some time. But rather than just have z-score square 1, z-score square 2, z-score square 3, independently, I add them up together. So this is a z1 square plus z2 square plus z3 square. And this z3 square is square square. Sum 3 of them together, okay? And that will be my L 10,000. Okay, I'm done. But let me lock the value and pay special value. Okay, so people, think about it for 1 second. Okay? I know that if I only have one z-square, it stretch out to 17. Let me redo it. Okay? This is a 10,000 number. And then, let me do a insert plot. Yeah. Okay. So, this is one z-square. Start from here, passing 5, stretch the elbow, probably somewhere around 3, right? Right? But then stretch somewhere around 17. Okay, so that's one z-square. So people don't just, copy paste. What do you think if I have 3 z-square, lump them together? This is my new observation. It's not just z1 square. It's z1 square plus z2 square plus z3 square. What do you think about a histogram? This histogram will be like this, or will be stretched out even more? Which way? Huh? Yeah, because now we basically said that yeah, still like the central limit theory, it's the power of the lump. The minute you start lump things together, we should see how it looks. I'm not going to turn them into percentage because that could be a good homework for you. So just data, data analysis, histogram from L1 to this much. Okay, so I did not log the beam, so usually the first observation is 1. I just ignore that last. If you log the beams, 0 to 1 to 2, you won't waste any of the. But since I'm teaching while I'm talking, yeah. So you guys see? First of all, originally it's kind of start from 0, right? Now it push out a little bit. And the other thing is that it stopped from 17 now to 20 something. So it's basically like this, okay? You can consider this. The distribution is the sandstone. Total area under the sandstone, the dome is what? 1, right? So the more sand you have, the sandstone is not as, the kurtosis, the sharpness is not as high. It tends to what? Crumble further out. Okay? So now let's back to our things. So if I have chi-square 3 here, our average divided by a bunch of the degrees of freedom. So up here is, say it's only 3. Here I have what? 12, right? So now our question really becomes that, so I have some z-square upstairs, I have some z-square downstairs, okay? So this z-square over z-square. It's kind of, they're the same dome up there and the same dome down here. So the outer bank conservation try to figure out that, do we have enough sand to cover the area? So let's first do the mechanics first. So rather than using only 3, what if, okay, I'm using 15 of them. Okay, so 1, 2, 3. Squiz. Okay. 1, 2, 1, 2, 3, 4, 5. Okay. Control C. Oh well. 1, 2, 3, 7. So that's 14. No. How many do I need? 12, right?
I thought you said 15.
No, hold on. I need to double check. The error term, how many is 3 divided by 12? So upstairs, pure randomness is 3 chi-square. Random. Downstairs is 12. Should be 12. Yeah. The homework I give you is not 4 by 4, right? The homework I give you is 5 by 5? 5
by 6.
5 by 6? Okay, 5 by 6 means totally how many degrees of freedom you have? 29. And then how many treatment you have? 5. So the degrees of freedom for your chi-square for upstairs should be 5 treatment, right? Just 5 minus 1 should be 4. And how many error term degrees of freedom you should have? 20, 25, or 29 minus 4, 25. Yeah, okay. So now we're doing the same things. So how many do I have here? I think I got too many. 14, so kill 2. Okay, so now the next thing is I need to sum the 12 together. Okay? And now, if I sum this 12 together, I have a chi-square 12 established. Oh boy. Okay, so once we establish this chi-square 12, same thing, usually I lock it, so the value, pay special value. Okay, so now, if I do a histogram here, speculate again, what will happen to the semi-dome? Further out, and the peak also further out. Agree? Okay. Yeah. This is something I like about Excel. You know, what you see is what you get. From AB1. Okay. So if you plot this, yeah, you can tell it's further out now. Okay? Okay. And, well, don't take my word for it. Let's go to Wiki. Chi-square distribution. And look at the chi-square distribution. Do you see that? K is the degrees of freedom. 1 degrees of freedom is the yellow one. 2, 3, 4, we got to 9. And then we got to 15, 12. You see that this same thing is kind of like, right? Landslide, moving to right directions. Everybody see that? Yeah, so, you know, what's chi-square? Chi-square is landslide, right? Okay, now we say that if I have a 3 degrees of chi-square here, and then a 12 degrees of chi-square here, and then all I care about is, hey, there's some landslide in the F. upstairs. There's some landslide downstairs. There's two different landslides. If I said that I would like to know that, here, let me put it this way. If the upstairs and downstairs are exactly the same, so it's kind of like, oh, you're here, I'm here. You're here, I'm here. The ratio is always 1. Then, there's no detectability, right? It's basically proportional. But if your downstairs stretch out more, the upstairs is tighter, well, I have to play with it. So you just said that, okay, I would like to have F statistic. Okay, let me put this down first. This is chi-square 12. And now we would like to do a chi-square over chi-square. Okay? So here's the treatment chi-square over error chi-square. Okay? Everybody agree with that? Wrong. The equation is wrong. Look at here. Look at here. We need to justify by what? By their degrees of freedom, right? So, something here, I would say, hey, you can landslide that much is because you have 3 degrees of freedom for you to abuse. And in the denominator, you can landslide that much because you have 12 degrees of freedom you can abuse. And of course, why I have to justify by the degrees of freedom? Because the more degrees of freedom you have, the flattened you're going to be. So I need to worry about, how many do you have? So once I do that, okay, now I have my F statistics done. Okay? And this is my F statistics. And next things is I would like to plot my F distribution of 3, 12. Oh, not this guy. This is nutty. No, I need to do data analysis, histogram. AB, no, should be AD. Okay, and then if you do that, you can have a histogram. This is your F distributions histogram. Okay, and the questions what we really want to have is that here is the ratio of 2 F statistics. You can tell majority of the value before the elbow point is about 20. So the ratio is about 20 is pretty big. Beyond 20 is not very likely, right? The ratio between the two values. Beyond 60, beyond 80 is what? Almost mission impossible. So, what we're really trying to figure out is that what is our observation we have? Okay? So, our observation F statistics, okay, is 8.53. So you basically said, hey, it's 8.53. Based on my experiment, big enough. So if my F statistics at 8.53 is far, far away on the right, means that tail value is tiny, tiny. Then I should say that, it's almost like, here, I have a mountain here, right? And then I basically said that majority of the stuff is here. It's getting less and less likely, less and less likely. So I'm basically trying to say that how less likely to have that observation. If it's, the probability is so tiny, that means that it's almost, how did I get this one? I guess this one's through randomness, right? I did not run any experiment. I start from bell shape, square the bell shape, and then sum the bell shape, and then sum the square of the z-square bell shape, a bunch of bell shape over a bunch of bell shape. So everything I do so far, all this, got anything to do with the experiment? No. It's just basically said that let's just try by chance. I try by having a normal distribution. I try by having a square of normal distribution. I try by sum of a bunch of normal distribution, sum of square of a bunch of normal distribution, and then I have them one over the other. So every time I did something, I'm really doing it by chance. By chance. And so the bottom line is, okay, if this thing's, okay, by chance, how likely can get this far? So now we just use the normal, not use the F distribution table. So by the way, here I'm just let you play with it, so it's not as accurate as the real things. So let me just use the real things here. Is give me an F distribution, F distribution. Excuse me. The F distribution, I have 8.53. 3 degrees of freedom in upstairs. 15? 12. That's just a test. Okay. And then, why it didn't work?
There's one more formula that's common for like cumulative.
Oh. Yeah. Now I remember. Excel, they separate PDF and CDF. Okay, so if we use CDF, should be 1.
Why did you use 8.53 again?
Oh, 8.53 is the F statistics, remember?
Okay.
But your homework probably is not 8.53, but...
Yeah, but it's just that example. So
yeah, this example, yeah, okay, we're on the same page. Okay. Okay, so now this value show 99, what was that? 9973. That means what? 99.7, you have to be 99.73 in that percentage in order to get that far out. So if that's 99.73 is the CDF value, then one minus means how much left. And the value is 0.0264. That value is called your p-value. So you probably remember your stat 101. The teacher always said the p-value less than 0.05, then it's significant, right? What does that p-value less than 0.05 really means? Means that your observation is so far out. In order to be that far out, we need to be 99.9 on the histogram, percentage-wise, in order to be that far out. So if be 99% out, how likely do you think that's by accident that far out to have a value that small? Very, very unlikely, right? You guys too young probably don't remember this. You guys know KGB? Yeah, and I used to joke about it. It's called KGB approach, right? The secret police. Did you do it? No. Did you do it? No. You keep asking the question. So sooner or later, no, you push them hard enough, whoever under the torture will say yes, right? And so the argument here is, okay, randomness, impossible. Randomness, impossible. It's almost impossible to be that small. The only way to be that small is what? Guilty, 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 guilty. Everything is saying that, okay, my p-value, say 0.002, means that I need to be 1 minus 99.999 in order to get that big. So, what is p-value less than 0.05 to you is the question. How likely by accident I can get this value? Now just put that down. How likely by accident I can get this value? Randomness, can you get that value? No. The chance to get that value is 0.00.002. So now, how likely do you think this value is very big? Beyond reasonable doubt. It's very unlikely, right? So how many people think that based on this, it's significant? Okay, then I worked for an insurance company before. I'll ask you this. Would you bet your life on them?
Yeah.
Cheap. Now, well, what I'm saying is that if you work out certain policy, say the COVID vaccine development, the p-value 0.002, probably still not small enough. You want to be 0.0000110, and then you said that's the one to use, right? So how significant is significant to be used? You need to be very, very big, or let a p-value to be very, very small. Okay, so before I ask you the next questions, you guys, can you visualize what I'm doing right now? Is F value, the 8.53 need to be as big as possible. And if 8.53 is as big as possible, your p-value should be as small as possible. Wiggle your finger if you didn't get it. Everybody get it? Can you see it? Okay? You see it, it's yours. But if you memorize this, you're not going to remember. I want this F as big as possible. I want this p-value as small as possible. They are related. Okay? And there's another way to think about this, okay? Desert Storm or the Eisenhower Normandy landing. Okay, military. Do you think they operate on a very, very big F value, very, very small P value? They do too. They need to, military generally, they need to figure out their risk before they say, let's have a Normandy invasion. But usually their value is not that small. Military will take risks. They probably, about Colin Powell says somewhere around 75% confidence, he will say action. Okay, but for us, especially for medicine, for electronics, your iPhone, you probably want this p-value very, very small to use. Okay, so I want you to think about it a little bit. We are talking about experimental design on the left beyond reasonable doubt yardstick on the right. We want the right side greater than the left side, beyond the reasonable doubt. And this is called F statistics must be greater than some F inverse statistics. Okay? And what is that F inverse statistics? Is this value. Okay? If I do a F IMV, okay? And then I said I want my value to be 0.999 or 0.95. If p-value is alpha is 0.5, 12. Oh. 0.05. So if your alpha level set up at 0.05, then as long as your F statistics is greater than 8.53, is greater than 3.49, you say actions, attack, do something. I believe beyond reasonable doubt, it's guilty. Okay? It's too small to see the other side too. Sorry. Here. This is F critical value for alpha equal to 0.05. Okay?
Do you mind showing us the formula for that?
Yeah, I'll do it one more time. F statistics, F distribution, p-value, F critical value. Okay? Yeah. Not only I'll show that, I would like you to regurgitate what I just, from last week till today. This is a good stopping point. Yeah, just, think through. Even from the first, why I need to randomize everything. And all the way here. If you work for, something at Triangle Park, they want you to run an experiment. This is your basic one you need to know. Oh, one more, okay? I told you guys I don't care if you discuss preparing your homework and everything. But you need to have your own Excel template developed by yourself. Because during the exam, I promise you, and you can ask, anybody took my class before, if you borrow somebody else's template, you're not going to make it. Because the problem is not just plug and play. You need to know what you put in. So you need to develop the template yourself. Not to mention I play tricks. Sometimes I random number in your exam problem. So your answer is going to be a little different from others. And just try not to just think that there's a shortcut. Oh, let me just borrow this Excel template. Okay? You need to think it through yourself. And also, can you guys see this? This can be used in industry. Okay, I don't know what kind of experiment you're going to encounter, but if you don't have SAS, this will work. Okay, so it's not like something just passed the class. You need to think it through. Okay. Any question for me? Okay. So now we're going to do this in a different way. We'll start saying that what if I want to look at a world not as a central station, subway station, I'm start looking at a world like a regression. Okay? And at the end, I'll say the regression and the central station, subway station will combine them together to find the optimum solution. That's called response surface. And so basically you have two different ways to look at a world. And why we don't have two different ways to look at a world? Again, use military jargon. Anybody heard the officer, sometimes they call it, say that, oh, you don't have the situation awareness. Ever heard that term? Okay, elaborate, what's situation awareness? Huh? Okay. This is not what Micah Hensley, the lady invented the term. Actually, I worked with her before. This is my interpretation. Situation awareness, three things. Where am I? Where I'm from? Where I'm going? A terrible military officer will be what? I have no clue where am I. Okay, and you ask, where are your enemy? I have no clue. Where are your friends? No clue. If you don't know where are your enemy, you don't know where are your friendly, how likely you think you know where to go? Not likely, right? So you will be in trouble. So, experimental design, to me, okay, is about situation awareness. And also, this is my engineering man. Okay, during job interviews, sometimes people will throw you a situation and say, "Oh, how are you going to resolve this situation?" Okay, how about write a 500 words essay? You do that, you're not going to get the jobs. Never give your boss an essay. A good officer should always turn a situation into multiple choice. Subway station A, subway station B, subway station C, and how significant, how likely it's going to be useful. So you tell your boss, here are 3 options. Here are 5 options. And if we do this, we'll get this, we do this, we'll get this. So if you can turn a situation into multiple choice, you know what you're talking about. But if you said, oh, the situation is very complex, it depends, and then you start writing a yada yada paper, you're asking to be fired. Okay? Christmas time is coming. Some people get Christmas bonus, some people will get a pink slip. Why? Some things, If you can turn everything into number, that's one thing. If you can, you're in trouble. Okay, so why we want to talk about the subway station, turn them into regression? Because if we turn them into regression, we have directions. And if we have directions, we have, what do we have how many of you have regression before? Done regression before? So what's in the regression?
1 equals mx plus b.
Huh?
1 equals mx plus b. You're going to follow.
Yeah. So y equal to a plus bx, right? And x could be a vector. And what does that mean? Intercept, and then the slope. And what does that slope tell me? Going that direction, the number will get bigger and bigger, will get smaller and smaller. So regression tells us the direction of improvement. Right? Right? So experimental design tells us how to build multiple choice. Regression tells us the direction of improvement. And we combine the two things together, we have what? Where am I? Where should I go? To get bigger or to get smaller? Right? Yeah, so yeah, it's not math, it's really way of thinking. So, let's do some simple regression. And let me see if okay. So let me use this approach. Simple regression first. I have a y. This y depends on two things: an intercept and a slope. If a is positive, means when I increase x, y will increase. A is negative, x increase, y will decrease. So every observation in the experiment depends on the slope and the intercept plus a epsilon term. The epsilon term, if it's before the experiment, it's a randomness. I don't know where they're coming from. After the experiment is the measuring errors. If the regression is like this, I'll have some leftover. And this leftover should be random. Okay? And I'm going to basically use the same data set you have before, or did I give you a data set, or I just asked you to? Oh, okay, I'll create a data set for you this time. So now, people, if I have a perfect regression, the B term and A term are really, really good. The epsilon term should be very small or very big. Okay, people in the back, avoiding eye contact. Let me try something. Young man, with a baseball cap. The epsilon term is the error term, right?
Is the what?
You see the epsilon term? Yeah. What's the epsilon term represent?
I'm not sure.
Because you didn't listen to me. What epsilon term really means? Before the experiment, who knows where, right? After the experiment, the difference is if I have a perfect regression to predict, I have a perfect A term and a B term, the epsilon term should be big or should be small? Small. Right? If the epsilon term almost zero, that means what? I have a perfect regression, right? Okay, so the epsilon term could be positive, could be negative, agree? So if I say that I would like to minimize all the epsilon square, means that I have a regression, right? Here. Imagine this table is a regression. Okay? Now, that's the wrong table. Let's use this table. Here's a regression table. Okay? So, if I have a regression table, some of you can sit a little further away, some of you can sit a little closer to the table. Okay? If you're perfectly right on top of the table, the epsilon is zero. And of course, if you're moving from the right, it's positive error. Then you're moving from the left, it's negative error. And then if, say, this is how everybody, I'm worried about the observation. Okay? If I have a table aligned this way, good or bad? Bad, because I have too many people on this side. If I flip the table this way, what happened? I have too many people on that side. The only way I can have a perfect table, perfect regression is what? Right in the middle. Some bigger, some small, but when you add them up all together, they cancel each other out. So what's regression? Regression is figure out how to minimize the differences. So every observation minus B, and, oh, this should be negative too, right? Minus B minus AX, okay? And then this square term, minus B minus A, okay? This is my objective function. And if I have a perfect A term and perfect B term, the partial derivative, first derivative of A term and B term should equal to 0. And so now look at this. Partial A, you don't have A, so it's summation Y. And then you have B, 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 how many B? N of them, so it's minus MB, or put a B on the other side, and then a bunch of X, summation X. So the first partial derivative of this guy equal to summation Y minus MB minus NA summation X equal to 0. Okay, so the first one, if you put negative here, can you see that this partial derivative end up with the first term? Can you see that? Same things. Partial L, partial B. So partial L, partial B. This time, okay, I need to worry about every term with the B involved. And so if you square them out, y square, it's the A minus B squared equal to what? A squared plus B squared minus 2AB. And then you'll end up with this equation. Now, I have two simultaneous equations. The determinant is n summation x, summation x, summation x squared. So this is the denominator, no matter I'm talking about the first one or the second one. And then the B term for the B term on the top, replace summation yx with MB, so copy here, and summation yx. Same things, put the denominator in the numerator, but this time replace the x part, or A part, with summation yx. You'll end up with this term. So now we have the equation done. Okay, now let me do it numerically. And I need you to do it numerically because I'm going to do something tricky later, okay? And first time you look at it, that may be a little scary if your previous statistics never actually done it. But after a few run, it should be fine. Okay, so let me how to download this?
You just have to click on it. You don't right click, you just click on the. Yeah, just left click it.
Just click on it?
Yeah. And then that link over there where it says download.
Oh, okay. Okay.
And then it should download in the box.
Yeah. Somebody told me this before, early sign of Parkinson, I don't remember. Where? I want to use the homework example last week. Oh, yeah. Let's use this one. Okay. So, okay. Okay, so suppose I have this many observations, just like before. Okay? So, huh? Oh, start from E. Yeah. That's my error term, huh? Oh boy. Okay. Data. Text to column. Next. Space. Finish. Okay. So, I have this many observations. Okay? And let's just say that, let me just find the average. Okay, but remember, okay, A, B, C, D, remember when we build the airplane, I don't really care A is big or B is big, right? But when you do regression, you basically say that, hey, I'm not gonna just using the nominal name, I'm gonna use a difference, I'm gonna use their order. Then you need to know the sequence or the order. Let me put this down, okay? Whenever you measure something, this is called measurement theory. In measurement, there are always 4 different types of measurement. I don't care if it's physics, biology, chemistry. Measurement level 1 or scale 1 is called nominal scale. Nominal scale is A, B, C, D. Okay, horse racing, horse number 32 versus horse number 23. Is 32 bigger than 23? No. It's just a number represent A, B, C, D. This is called nominal scale. The second order is called ordinal scale. Ordinal means rank. So, you know, I'm bigger, I'm taller than you, I'm older than you, you older than him. All we know is that there is an order. But how far apart? Am I 40 years older than you? You 5 years older than him? Doesn't matter. All I care about is I'm older, I'm heavier, I'm stronger. Basically, you can rank them. This is called ordinal scale. Okay? And the third scale is called interval scale. Interval scale means the distance matter. I'm 40 years older than you, you're 25 years older than him. Doesn't really matter, you're 1 year old, he's 26 years old, and I'm 65 years old. Because it could be you're 10 years old, and he's 35 years old, and I'm, plus another 40. Interval scale, I only care about the distance, but I don't care where is the zero. So in other words, is that all I care about is I'm older than you by 40. It could be 140 versus 100, could be 40 versus 10. The only thing we measure is what? The interval, the distance. No zero. The last one is called ratio scale. Ratio scale means that you have absolute zero. And if you have the absolute zero, you can put percentage, you can put ratio. In your lifetime, have you ever heard absolute zero? When? Temperature, Kelvin, right? Negative 273. What's so significant about negative 273? Huh? Means there's no energy. it's a theoretical temperature. In theory, through regression, we don't know if they're actually absolute zero. But when it's absolute zero, there's no energy. If there's no energy, with or without quantum physics means what? There's nothing can be measured. There's no mass, there's no temperature, there's nothing. Ratio scale. Okay? And in this class, if we have other class. I taught Bayesian network sometimes. Then we'll talk about ratio scale. In this class, we're focusing on nominal scale and interval scale. And regression is interval scale. Why regression is interval scale? Because we have the slope. And when we have a slope means what? Along this table, if I move 3, I can do 2, 4. That's what? Slope, right? So in order to do regression, because we need to have the slope, and if we have the slope, we know positive slope for improvement, negative slope for, one for increase, the other one for decrease. Okay? So now let me fake this one. So I'll call this is my level 4 because they're all big. 4, okay. And I'll call this one my level 3. This one is my level 2. And of course, the last one is my level 1. Okay, so now I turn my subway station into the lowland subway station, highland subway station. How did I decide that? We can discuss that later. But right now is basically I turned that 4 level into 1, 2, 3, 4. And then if you plot it, you basically see this. 1 to 2 to 3 to 4. Okay? And if I change the scale, moment axis, if I turn them into, say, 1.2, a little more, 1.5. Okay, just by looking at,
We have about 5 minutes left.
okay, so, so just think with me. Based on this, 1 to 2, 2 to 3, 3 to 4. So now I'm in a subway station, the lowland underneath, highland above the somewhere, right? Okay, just by looking at this, people, what do you think? The slope should be positive or negative? Positive. So what it means is that moving from 1 to 2, some improvement or increase, 2 to 3, some increase, 2 to 3, some increase, right? So let me cheat a little bit. Excel, tell me what will be the slope. Slope of this and of this. This is the slope. And tell me the intercept. Okay? Now, of course, if you go out for a job interview, you just call Excel this way, nobody respect you, right? We need to go a little beyond. So how to go a little beyond is we say that there are some X and there are some Y. Okay, and I said y is abx. Okay, so the only reason, I can memorize the equation, but that's not important. I would like to use the sim notation, so you guys will follow the sim notations. Okay, the notation said, oh shoot. Notation said that I need to know n summation x squared. So n is number of observation. So the number of observation n we know is 16. And I have 16 observation. And then I have summation x. So summation x is a bunch of x summed together. And I have summation y. And look at the equations. What else I need? Summation x, summation y, summation x squared, summation yx times y. So I will do this. X squared and x times y. X squared is this guy's square. X times y is this guy times this. And then once I do that, some things, I need to find the sum. Okay, so the denominator, or the determinant of the denominator is equal to, let me cheat, n times summation x squared, summation x times summation x squared. So d term equal to n is 16 times summation x squared minus summation x times summation x. So my determinant is 320. And then let me find my A term and my B term. My A term is equal to, okay, or my slope is equal to n is 16 times summation yx or summation xy minus summation x times summation y. Okay, and then if I use this thing, whole things, divided by my determinant, basically repeat this equation.
We know the determinant equation again.
Okay, but I promise, we'll be right back, okay? Just want to just say, first, everybody agree? I repeat, what?
We can't see it, Lord. Never mind.
1 second, I'll be right with you. But everybody agree with me that I can get the slope just like Excel get? So now, first, you have to say, yay, we get it. And then we go back, how we get it. First, figure out the D term, the determinant. The determinant is what? The n times summation x squared minus summation x times summation x. That's how I did it. And then the A term, first I need to have the n times summation xy times summation x, summation y, and you get the numerator, and the numerator divided by the d term, the denominator, you get this one. Okay? So what I'm saying is that I'm just following the equation, except I'm using Excel to illustrate it. Still have time, or I'm done?
You are out of time.
I'm out of time? Okay, so we'll continue this. And believe me, okay, things gonna get messier and messier. Start having stem intercept, different slope, slope, different intercept, and combination of different things means different way of getting situation awareness. Okay? Okay, see you next time.